The stage is yours.
Hi, so we're going to be talking about the PubGrub algorithm and porting it to Rust, building a flexible dependency solver in Rust. I am Jacob Finkelman, also known as EH2406. I'm on the cargo team helping to maintain Rust's package manager, and I also work at Amazon in the code artifact group. And thank you to my employer for the time to work on these presentation and come to this conference. My co-presenter is Matthieu.
Hello. So my name is Matthieu Pizenberg. I'm a French computer vision postdoc living in Caen. And I started this project of dependency resolution in Rust about a year ago, and I was really lucky to have Jacob joining me then.
So let's start by talking about the PubGrub algorithm, and we're going to start by talking about the problem that the past two presentations have been talking about as well. So we have dependency resolution. We want to provide to our users this solve function that takes a root package to build and some data structure representing the rest of the universe of available packages and returns either a solution, here's what you need to build, or an error message explaining what can't be built. Even if you slim this problem down to its core essentials, there is at max one version per some constraint called a package name. And every time you require some other package, that package must exist in your solution. You are already NP complete. And what this means in practice is that there is a performance cliff. For sensible, simple code, it will go quickly. And at some point, you will get complex enough that you have an exponential amount of time. And the question is, how close is your user base to that exponential cliff? Because hitting it, realizing it because of user reports is a really painful way to deal with things. As we have found it at Cargo and Conda has found and Pip has found, there are lots of examples of that. So why not use, if it's NP complete, why not use a SAT solver? Like, well, the past two presentations talk about the advantages of using Z3 and ASP respectively, but let's talk about some of the trade-offs there. Well, one is that we have literally thousands of potential packages, most of which are irrelevant to the build we're trying to build at the moment. So we want to read in data incrementally. So we're looking for an incremental satisfiability solver. Um, we also really care about the error messages. If something goes wrong, we want to explain to the user it was this dependency you had that created the problem, and here's what the problem is and what you can do about it. Also, we don't care if it succeeds. We don't want any solution. We want the best solution by some standard. Um, and so we kind of want a max sat solver. Um, the advantages of a globally max sat solver are two presentations ago, but uh, we definitely want some kind of optimization. And the one per package constraint is an XOR constraint, which many SAT solvers find very slow. So finding a SAT solver out of the box that's going to do all of this is going to be painful and difficult. So we're going to need to customize one anyway, learn from previous projects, but customize it. And this is exactly what Natalie Weizenbaum was asked to do for the Dart programming language. And she started with ASP and read through the theory and came up with three optimizations that are relevant to this one problem that make it different from the generalized ASP solver. So one is that when you combine, there's only one version per package. With version constraints, you have set characteristics. I can say that the intersection of greater than 3.0 and less than 2.0 is the null set without looking at what versions have been published. That makes a big O of n difference to every operation and every explanation you need to make. That matters. Also, a generalization of some of the data structures from ASP called an incompatibility can represent all of the data structures that our solver needs. In Cargo's current code base, we have an entire data structure that represents dependency facts and a data structure that represents conflict-driven facts. And translating between them is a source of a lot of our bugs. So she found one data structure that can represent all the facts in one place. Also, if you use one data structure that represents all of the information, then looking at that data structure, you have a proof of a problem if if you need to generate an error message. So the program can generate a human readable error message that proves why the solution was impossible.
And that magical data structure is called an incompatibility. And so basically what incompatibility are is a statement of a group of each incompatibility is a group of statements that basically can be interpreted as don't give me a solution that has this, that, or that. And each statement of an incompatibility is called a term, which is said to be satisfied if it's evaluated true or unsatisfied otherwise. And the goal of dependency resolution based on incompatibilities is to never reach a point where all the terms of one incompatibility get satisfied because we reach a conflict. So incompatibility can express, for example, the initialization of our algorithm. So if we say, don't give me a solution that has not picked our root project, it is an incompatibility that says that we need to pick the root project. An incompatibility can also express dependencies. So for example, if package A depends on package B, we can say, don't give me a solution that has A and not B. And incompatibilities can also help us detect conflicts during dependency resolution. So if we start with this simple example where we have our initial project that depends on two packages, package A and package B, both at version 1. And those packages have their own dependencies. So package A has no dependency and package B depends on another version of package A. So let's say we're in this situation and we keep those incompatibilities describing this situation. So if we start the algorithm, we start with the root incompatibility and we pick root. Once we do that, some of the terms get satisfied. So we have other incompatibility to unsatisfied. And so logically, we say, for example, here we get to the dependencies of root and we say we'll have to pick version 1 of A. Great, we do that. And so another term gets satisfied. Then we say, okay, now we have to pick version 1 of B according to the second dependencies of root. And if we do that, we get to a tricky situation because once we do that, we reach a conflict. And so what we do is that when we reach that conflict, we take that conflict as the initialization of a procedure that we call conflict resolution. And what we do is we go back in time, we look in a special way at the root of this conflict, at the previous choices that we made that resulted in this situation. So if, for example, in this case, we had the root package that depends on package B, and B key depending on package A at another version. So basically, you can derive a new fact, which is that root package depends on version 2 of package A. And we go back again, we find another incompatibility saying root package depends on version 1. But since we have root package depending on version 1 and version 2, it means that root cannot be selected. And this forms what we call a derivation graph. And you can derive an algorithm that reads this graph and outputs a very human-like error message. And that's great for users of our solvers.
So now let's talk about our porting it to Rust. So as discussed 2 presentations ago, it's very nice to give users choice because different package managers have different constraints. So our algorithm is deterministically takes all of the facts that have been presented to it and combines them and works through the logical implications thereof, and every time it has a set of candidates to pick from, it asks the user's callback which candidate to pick next, and every time it has picked a new version that it has never seen before, it asks the user's callback for what dependencies that that package version has. By making this flexibility, a uh, a user can provide their own form of at least local prioritization um, by picking candidates that, for example, are in a lock file first, or that have the fewest number of versions available, or that have the fewest number of dependencies for the version they're going to select first, whatever they want to optimize for. Um, by picking the dependencies, those can be stored in arbitrarily complicated formats or can have slightly different semantic meanings from the ones that our library interprets them as. And so this is one of the key callbacks in the 0.2 API called choose package versions. Our library is going to give user code a iterator of packages and the constraints we know about those packages. And then your library has to, or your code has to return to us which package to choose and which version of that package to choose. Um, so we iterate over the potential packages to pick a package. Um, you can use whatever heuristic you want. In this case, we're just going to pick the first one. Not a performant choice, but a good one to fit on a slide. Um, then you iterate over the versions that are available to find ones that match the constraints that PubGrub has already found for this. Then from those, you get to pick which version you want us to try first or try next. In this case, we're choosing the last one. I would, if it weren't a slide, pick the newest one or the oldest one or one in a lock file. So that is the flexibility you can get by choosing the prioritization function. You also get a lot of flexibility by choosing the representation of dependencies. For example, many dependency resolvers have optional features, optional build flags. So how could we represent that in PubGrub? So we can make a feature if we have a package A that always depends on B, but only depends on foo if the optional foo flag gets passed, we can represent that to PubGrub as a package A that always depends on B and a package A with foo that depends on foo and A. And this is a way for PubGrub to have the same semantics that our larger solver has while maintaining the great error messages and other features. Another complexity that real resolvers have that we have not yet handled is pre-releases. So the hard case here is, does 2.5.0 alpha match the requirement greater than 2.0? On one hand, 2.5 is greater than 2.0. On the other hand, it's alpha and you need to opt into alpha level software. So in many package managers, it depends. What it depends on the package manager. So clearly, we are going to need to provide some way for the user to add context to our incompatibilities. And we have a prototype for how to do that is working correctly, but we will need time to make sure that it is easy to use correctly and that it is easy for people to test to make sure they have used well correctly. And that gets us to, we care very much about correctness. We test in addition to localized testing, we test end-to-end correctness on all of the published packages of Elm, certain hard cargo cases, some randomly generated uh, synthetic data, and we test various end-to-end properties. We test, most importantly, that we get the same answer you get with one of the SAT solvers, at least to whether it error messages or not. We check that our algorithm is deterministic, and we check that changing prioritization does not change the correctness of the algorithm. It either errors or does not error the same. We have more properties, but we don't have time to get into them. Happy to talk later.
And of course, correctness matters, but speed matters too. So we make sure when we are developing different functionality and improving the algorithm that the speed of the solver always is always good. So basically, one use case important for us, because I started this project because I had a use case for this in the Elm ecosystem, was to solve dependencies in the Elm ecosystem. And in the initial version of the solver, version 0.1, we solved all Elm versions package dependencies in something about 2.5 seconds. So it was not a mean, it's like solve all the versions. And then with the help of Jacob, we did a lot of optimization and we reached some level of speed that are, I think, pretty impressive. And we are like going with a good trend, I would say.
And we intend to keep that trend. So you can look at our project on GitHub. We also have a very excellent guide made by my co-presenter. We have a chat space on Zulip, and we would love to hear about other questions or interactions, or keep the conversation alive.
Awesome. Thanks for the talks, folks. We do have time for questions for a change. So I am looking at the chat and I see only one, which, I don't see any yet. Well, I have one, which I'm going to directly type into the chat. One moment. Let me paste that in. Nope, that's the wrong one.
That was for the other presenter.
Yes. There we go. How well does PubGrub handle conflict resolution when dealing with optional dependencies? This was one of the things that we faced a bunch of issues when we were writing pips resolver, of the optional dependencies causing the wrong kinds of backtracking in the resolver, and it being like, no, that's not the thing you want to backtrack on. You want to backtrack on the thing above that. So
that is an excellent question, and that is one of the reasons I got interested in PubGrub, is that I suspect there are more lurking bugs in Cargo about the same thing. And so I wanted to be able to start from a solid foundation. And so PubGrub itself does not know about optional dependencies, at least at this time. And so all of our SAT solving makes sure that it is doing the right thing and backtracking the right amount. And then we are adding optional dependencies as a user level semantics on top of that. So we know the solver is correct, and it's just, did we map our concepts correctly? Now, what that does to error messages, we will have to figure out when we have real examples.
Yeah, because it's basically, so what the example said in the slide is basically that it's up to the user to tweak, I would say, the set of package names to make sure that they can express optional dependencies or other properties just by changing the set of package. And so the solver doesn't change. It's just on the user side. And we have a guide that helps with some of those cases to help people start with a good foundation for this situation. We don't hear you.
Yes, you don't. Hey, it was my turn, okay? Yeah, that's good. Let me see if I have more questions. I do have one from Todd, which I'm going to quickly try and copy over. And I think it's too long for the banner thingy that we have going on. Yes, it is too long. Let's see if this works.
Multi-objective optimization. Redundant versions.
So the point, so we do local optimization up to the user, tell us which one to work on next. Global optimization is something we had not thought thoroughly about until the talk a couple of talks ago, and so we'll definitely come back to. But one option that is on the table, as Conda used to use, is that you can do it iteratively. You can add constraints that you find a solution, you add a constraint that has less of your global property than the constraint you found, and if that has no solution, you have found the optimal solution. This takes multiple iterations, but we're running fast enough that might still be an efficient solution. It's something we need to think about.
It's not very elegant, but yeah.
And how big are these graphs usually?
So I don't have the numbers to hand. Elm tends to be pretty small. Cargo tends to have larger graphs, but we're happy to work at any scale. I can say that to solve all packages currently published on on Cargo's package manager, crates.io, takes about an hour and a half, and we intend to get that faster, because you can't optimize large cases till you can run up large cases fast enough to run them in a profiler. So it's an iterative process.
Sounds cool. Well, that's all we have time for, folks. I wish we had more time for more questions because more of them are starting to roll in. So if you could hop in over the
We will.
Element chat, that would be great.
Thanks
Thanks
you so
again.
much.